friends with whom we were doing our compass experiment, and then we continue now with the Drell-Yan. And congratulations with your new building. Well, for you it is maybe not that new, because when I was last time here in Lisbon, you were still in the old building, near to the closer to the downtown. But this structure I found really very nice and convenient. So thanks a lot, Katarina and colleagues, for invitation. And yes, I will try to make some short excursus through the very selected topics of compass when we were involved. And then I will smoothly come to the idea and what was the driving force of our new idea for this new experiment, which is called now AMBA, which is to some extent successor of the compass. So just to orient you geometrically or geographically, we are talking about CERN North area. This is also known as Laboratory 2. So we are here in the experimental area, which is called EHN2, where we have extracted beam from the SPS. And actually, in this very experimental hall, there was a number of famous experiments. The NA4, EMC, NMC, SMC, compass, and finally AMBER took place in this very experimental hall. And basically, most of those experiments, they are known because of their contribution to the study of the proton structure and the proton spin structure, because you remember about this famous proton spin puzzle. It was really discovered here. So saying that, of course, spin is a very important quantum number. So better we understand how it works. And just to remind you that it is our current understanding of the nuclear spin, how it is decomposed. But initially, people were believed that basically the spin of the proton contains in the spin of the partons. And when the first measurement has been done, so you were expected to measure 1/2 of the proton spin, but it appears to be much less. So then this hypothesis failed. So then the spin of the proton is not only the sum of spins of the partons, which are staying inside of the quarks, inside the proton, but as well there is a gluon component, and as we understood later, there is also contribution from the orbital angular momentums. And actually we did, I have no time unfortunately to review the whole program, the whole compass achievements, but the compass has contributed greatly in the more precise data on the fraction of the proton spin which comes from the quarks. As well, together with Rick, we succeed to improve our understanding on the fraction. Unfortunately, it is somehow anyway, so we did as well very good job on the measurement of the fraction of the spin of the nucleon which come from the gluon, and basically, we understand nowadays very well that this is those three components, so contribution from quark, contribution from gluon, and angular momentum, which have to in the end to give you this 1/2 of the proton spin. The only unrevealed part of the spin, it is orbital angular momentum, because it is difficult experimentally, but we have quite clear idea how to do this, because in order to create orbital angular momentum of the partons, you have to take into account spin orbital correlation. So in order to reveal this missing part of the proton spin, you have to go you have to admit non-zero transverse momentum of the quark inside the nucleon. So you have to go and study three-dimensional structure of the proton. So as I said, first two components, we are doing well. We know them with a good enough precision. And we have a recipe how to get to the third component. So to our mind, the spin crisis is over, because we understood what are the parts which compose the proton spin. And we, as I said, we know the recipe how to have an input on the only missing part. You have to study 3D structure, and you are aware that the full description of the proton of the parton distribution inside the nucleon is given by the Wigner function, which is 5-dimensional function. Unfortunately, it is not experimentally accessible. So we deal in experiments with two types of functions. This is TMDs and GPDs, and they are both measurable. And in order to go to the TMD sector, you just integrate Wigner function over the transverse position of the parton inside the proton. And in order to go to the GPD sector, generalized parton distribution, you integrate. This is a transverse, the transverse position of the parton inside the proton. And here you integrate over the transverse momentum. And both those are measurable, especially for GPD, it is not really easy accessible experimentally, because you have to go into the exclusive measurements. For TMDs, it is a bit simpler, and if we are talking about access to the transverse momentum dependent PDFs, you can use, in principle, different probes to have an access on TMD. This is a semi-inclusive deep inelastic scattering, Drell-Yan, proton-proton collisions, E+ and - collisions. And here in my talk, I would like to pay special attention to because when you measure how you have an access to this kind of transverse momentum dependent functions, you measure asymmetries, because you have a pre-selected direction in your experiment. This is the orientation of the spin of the target. It is transversal, and you have your projectile, which might be or muon or pion, and then you measure asymmetries. First data set you take with one orientation of the spin of your target, then you invert spin orientation, and you repeat your measurement. And when you basically subtract one cross-section from another, you measure asymmetry, how your cross-section depends on the various angular correlations. And from various angular correlations, you can have an access to the so-called TMDs, which are leading order parton distribution function. And the most important for us, this is so-called Sievert's TMD, because it appears in leading order once you admit non-zero KT, non-zero transverse momentum dependent of the parton inside the proton. And it is very important because if it is non-zero, then you can use this Sievert's function, measuring Sievert's function. You will access in model-dependent way, unfortunately, to the orbital momenta. So you will, if you measure, if you know Sievert's TMDs, this will give you an input on the only missing the term of the proton spin. This is why that was important for us to access this Sievert's function. And actually, we did it in several experiments, and that was a nice journey. which was started very unexpectedly for us because when we start this measurement, the measurement of the Siever's function or attempts to measure to access Siever's function, there was a Hermes experiment which was running in DAISY. And it was similar but different experiment because they were using the polarized target, not solid state polarized target, but gaseous target and electron beam. And basically in the same time when we start our campaign on measure transverse momentum dependent PDF, they did the same measurement using hydrogen polarized target, so proton. Contrary, we decide, look, they do hydrogen, but we are better, we can do deuteron, which they cannot do. And the result was very unexpected because Hermes, after the first experiment, they saw perfectly non-zero asymmetries in their experiment on the proton, on the hydrogen. What we see, zero on our deuteron data. Immediately you start to have doubts. How can it be? So how can they see, in effect, how they can see this non-zero Siever's function, and we basically measure zero. That was one and a half year of quite hard time when we were trying to understand what we did wrong. But fortunately, there were clever people around, like Mauro Anselmino and his colleagues from Torino. He is a Siri person who was one of the reference persons for this TMD physics. And they scratched a little bit their heads and they said, no, look, you are okay. Why? Because the Siever's function is flavor dependent. So if you measure the Siever's function on the deuteron, as we did, you have two components on U and D quark which just compensate each other. And this is not the case of the proton measurement. Okay, so that was very positive news. So we know that seems we are doing everything correctly. And this zero, the zero Siever's function, the result on deuteron target is what we simply have to expect. But still we were not sort of totally happy until we repeat Hermes measurement, but on in compass using not deuteron polarized target, but hydrogen polarized target. And you see, also we saw this perfectly non-zero result, which is exactly what would you expect in case you measure on the proton. So we are happy. There is a final result of Hermes. There is a final result of compass. We see the same, nearly the same effect when we expected it to see. Perfectly confirmed that the Siever's function is non-zero. So there is a hint that there is non-zero contribution of this third term of the proton spin. But what we noticed that in spite of we have similar results with Hermes, still their experimental points are lying systematically higher compared to the compass, because the open circles here Hermes data and the closed circles compass. So we start to think why can it be? Because there was clear systematical difference between their results and us. And we find an explanation because it is two different experiments, and if you see at the average Q² value in the every beam of X of our measurement, the compass Q² value, so because we have much higher beam energy, systematically higher with respect to Hermes. So the first idea we had, then these TMD functions can have to be Q-square dependent, so there is a QCD evolution of those functions, depends at which Q-square you probe them, the amplitude of this function have to be different. So that was two very important lessons we learned from the first bunch of measurements we did with compass. So TMDs are flavor dependent, first. Second, they are affected by QCD evolution. And it seems it plays a significant role. Why it is important? Because as Katarina mentioned, at some point, yeah, that was all nice and good to have these measurements and to believe that what we are doing, it is TMD physics, that effects which we are observing are somehow the underlying phenomenon is TMD, but you never know. Because there might be different interpretation, there might be higher twist, for example, contribution or whatever. So people start to say, okay, we should probably think of how we really test whether the underlying mechanism behind all these TMD functions and symmetries are really TMD functions. And luckily, we found a way how we can test it. Because of this unique feature of the interplay between the Drell-Yan and CDS process, and because of the unique feature of the Sievers TMD, it is time reverse. It is time odd. So that means whether you access this symmetry in CDS or Drell-Yan, the sign of your symmetry have to be simply inversed. So, so in case all what we thought, it is really generated by the transverse momentum dependent functions, then we have to observe this sign change when we access the same physics quality from Drell-Yan or CDS. And this is really when we start to discuss with the theory colleagues and we say, look, you tell us it is extremely important, but if, for example, we do not see this sign change from Drell-Yan to CDS, what would it mean? And they said, of course, that that wouldn't mean that the whole QCD is wrong. But that would mean that the old data we have collected so far in Compass, Hermes, at RIC, we just totally misinterpret this data. So the underlying mechanism behind all these asymmetries we have measured, it is not TMD, but something else. So this is why we decide, and we have this unique opportunity, and this is the newly constructed bridge I was born in Dubna. It is the Joint Institute for Nuclear Research, probably you know. And this is a newly constructed bridge, and it is sort of, yeah, big event. So, and this is a bridge which, in terms of compass, just connect two banks of the same river, so Drell-Yan and CDS, and we can do these two measurements in compass, basically using nearly the same spectrometer. This is absolutely unique feature because we can have extracted muon beam and high intensity hadron beams. And just to remind you about the Drell-Yan, it is a very simple process when you have just annihilation of two quark anti-quark pair with the production of two leptons in the final state, and X we unfortunately don't see because we have to place an absorber in our spectrometer, which is fixed target experiment. Otherwise, because it is very small cross-section process, you know about this. So, in order to have sufficient luminosity to access the physics we wanted to access, we have to shoot on our spectrometer with high intensity, real 10 to the 8 per second hadron beam. it is really high intensity. So in order to not make our spectrometer blind, we just place the Hadron spectroscope, the absorber in the front of the spectrometer. So we are not able to see the X. The only thing which we detect in the final state, it is di-muon pair. And when we planned this experiment, we, of course, being aware about the QCD evolution, that TMDs are the sort of affected by the TMD evolution, we have started to contact our theory colleagues, asking them, what do you think, what kind of effect, what is the amplitude of effect we should expect when we are doing our Drell-Yan experiment, because Drell-Yan, it is always low statistics experiment, so if they would say us it is on the level of the fraction of the percent, then it would be not accessible for us at all. And we got a full spectrum of predictions, because different theory groups, they use different models for the TMD evolution. So, and we had depending on whom we were asking, we were getting from, say, 10% down to 3%. So it is a factor of nearly 3 to 4 in the difference in the prediction. And this is what we knew, that with our expected statistics, we probably can get, we can see an effect of the level of 5%. So that was very much at the limit. So in order to make sure that we can expect in our kinematical range, which we can access in Drell-Yan, the reasonable effect, what we did, we took our CDS data as we have them in COMPASS, and we stick to the I can get there, to the upper beam of this distribution, which would exactly correspond to our beam and Q square, which is accessible for the Drell-Yan. Because you know, in order to stay in continuum in Drell-Yan, you have to avoid J psi peak, so you have to go in the Q square from in the range from 16 to 81. So we just select from all our CDS data, which are lots of there we have no, in CDS we have no problem with statistics. But we stick to this very kinematical range where we know we will measure in Drell-Yan, and then we extract the value of the Sieverts asymmetry in that very range. And we make ourselves convinced that it is non-zero. So that means it is very at the limit, it is on the level of few percent. So this is anyway something we can try to access in the Drell-Yan experiment. So, and yes, as Katarina said, we were preparing this Drell-Yan experiment for 5-6 years from the approval time. And when I was talking about this Q square range, Q square range, it is just m square, so the squared invariant mass of the di-muon. This is exactly where we have our Drell-Yan events, because in the rest of the spectra, they are polluted, contaminated by the J psi signal, the open charm signal, combinatorial background, and all the rest. So we did this experiment. More or less everything went as expected. And this is our final results, which we are still not yet published, but about to publish. This is a Sieverts function as we saw it in Drell-Yan in the various beam of our kinematic variables. And the most important is this point. As I said, it is hard to get to high statistics in Drell-Yan, but pay attention. So if the hypothesis of sign change would be true, then we would have this point upstream with respect to zero line. And where is the most of the theory predictions indicated? If they would know sign change, we would have this point here. So we cannot, after having done this experiment, in compass, we cannot declare that at 3 sigma level, we declare the natural limits in the luminosity, because we cannot have more higher than the beam muon beam higher of given intensity, and this is as well the case for the hadron beam. So when we start to consider the science question to be addressed by amber, we exclude basically spin from this consideration, because we think that proton spin and structure are pretty well known by now. There is a number of facilities which will be running in the near future who will provide additional, they are already running experiments like Jefferson Lab Rig, and we still have some analyzed. And then there are future facilities which would provide really this missing luminosity, which is unreachable by compass-like experiments. So this is why we decide to widen our sort of horizons of our physics reach. And yeah, then generally speaking, the CERN was always telling to us, look, if anything, what you are talking about, can be done somewhere else, but at CERN, it has to be done somewhere else. So at CERN, we have to do unique measurements, which can be done only at CERN and nowhere else. So this is why now I'm coming to amber. We basically start to think about the amber physics program from scratch, looking around and thinking where we really can do the unique job, but which is, by the way, would be highly expected by the hadron physics community. And we are still in the same experimental area. This is the complex of the extracted beamlines in the north area. And yes, what simplify our thinking very much, it is uniqueness of our extracted beam. I remind you that basically we have SPS, which shoot with a 400 GeV proton beam in the production target, and then you can extract toward amber high intensity hadron positive and hadron negative beams. Why hadron positive and hadron negative? Because we cannot separate by our magnetic system lens, by the system of magnetic lens, different species. We can do it only next to the spectrometer using our Cedar-Cherenkov detector, because our positive hadron beam, it is mostly dominated by protons with a 25% of pi pluses and some few percent of k pluses, and negative beam is dominated, as it is indicated here, by the pi minuses, nearly 95% and few percent of the kaons, k minuses and antiprotons. So, and this is a characteristic of our beams we can have in the spectrometer. There is no similar hadron beams elsewhere in the world, just because of its intensity and the energy. We have excellent muon beam, and also for calibration purposes, mostly we use the electron beam. So having these beams, unique beams, it was quite easy to construct unique physics program. And while we were starting to think about the science question for amber, we realized that amber really can play a key role in the understanding of the very important phenomena which is called emergence of the hadron mass. What does it mean? Because you know that was extremely important to have discovered the Higgs boson. That was great. Everyone was happy because it is really what everyone would expect. This is a confirmation of standard model. But Higgs mechanism is responsible for the generation of only less than 1% of mass in the all visible universe. Less than 1%. Then Higgs mechanism cannot explain neither nearly masslessness of the pion, nor why proton is so heavy. So nothing tells, even if you discover Higgs, this doesn't help you to explain from where this 99% of visible mass of the visible universe came from. And this is exactly what we are trying where we're trying to produce in input. You understand it better, because clearly that to our mind, the answer on this question from where this 99% of mass of the visible universe came is lying somewhere in the standard model. Moreover, we are convinced that it is lying within the QCD. Why? Because of this unique sort of nature creation, which is called dynamical mass generation in the continuum QCD. This dynamical mass generation is really truly mass from nothing process, which is explained by the simple feature of the gluon, because every single gluon can emit and absorb other gluons. And this is a sort of chain reaction. So starting in the beginning from the massless gluon, while it becomes physical, when it goes in the infrared, it is going to be dressed by sort of the cloud of the massive gluon fields, and it became heavy. But what is extremely important, it is not becoming unlimitedly heavy, or but it saturates at some point. So that means that gluons, while became massive, it really became, it acquired limited mass. Because if they would not be limited, then you see your gluon would just drop down, crushing everything, because it would become infinitely heavy. This is not happening. And the same effect is working as well for quarks, because quark can emit gluon, can absorb gluon, so also quark became dressed by this cloud of the massive fields, and while became physical, it acquired mass. And this is what we believe stays behind this emergence of the hadron mass mechanism. So thanks to this effect, dynamical mass generation in QCD, because it is QCD which allows this mechanism, you really, starting from the massless fields, while they became physical, you gain mass. Problem here, as always, you know, all is nice and perfect, and unfortunately, you cannot measure propagator, gluon propagator in the experiment. You are only deal with the final physics objects. So, but what you can do then to make sure that these effects is underlying effects? You just take calculations which were obtained in continuum QCD or on lattice, and you compare with what you measure experimentally. Because now we have, thanks to our CERN colleagues, we have very solid methods in lattice QCD calculation or calculation in continuum QCD, which can predict the PDFs or pion distribution amplitudes. They can predict the radii of your objects you are going to study, pion, kaon, proton. And of course, in QCD, you can also calculate the excited spectrum of the, for example, kaon or the strange mesons. And this is exactly what we are going to do in AMBA. In our experiment, we are going to do all these measurements and compare them with the calculation in the continuum QCD in order to make sure that these calculations are really experimentally confirmed. So then the all mechanisms which are existing or which are making the core of the continuum QCD really describe our understanding, properly describe our understanding of the mass generation in the visible universe. And what is also important to say here that, it is extremely important to not only to study the proton structure, as I said, apart of the fact that it is well known, well studied, but we have to understand why, for example, this difference in the mass, in the physical mass between the pion and proton, because you know that proton consists of 3 light quarks, pion consists of 2 light quarks, so you would expect 1.5, factor 1.5 difference in the mass of these 2 objects. What you see experimentally, it is factor of 7. How can it be? It is exactly because of the internal dynamics of these 2 objects, which are very different. That means it is not enough to study proton and proton structure in order to understand the phenomenon of the emergent mass, but you have to study as well pion and kaon. And this is exactly what we are going to do in number by using number of probes, the same Drell-Yan, J production mechanism, photon production, diffractive scattering, and elastic scattering inversed elastic scattering. So, as Katarina already said, we have submitted the proposal for phase 1 of AMBER, which contains proton radius measurement and matter production cross-section and pion and kaon PDFs and Drell-Yan and J in 2018, and it was approved by research board in the end of the 2020. And now we are going ahead with the preparation of second phase of proposal, which we intend to submit to CERN SPS committee sometimes in 2025. Talking about Drell-Yan, historically, your laboratory was involved in many Drell-Yan activities, so you know that there is the existence of the very old data, Drell-Yan, in pion-induced and kaon-induced factor. But all these experiments, they have been done so long time ago that we cannot use this data anymore because over the past 30 years, we start to understand much better what is going on in physics. So with our new knowledge, we would be happy to reanalyze this data, but it is not possible because the data are not basically there in the accessible form. It is one point. Second point, sometimes the experimental data is just contradictory. And there are discrepancy between the data of various experiments. And these data were mostly taken with a hadron negative beam and on heavy nuclear targets. So all these tell us that we have really redo all these measurements, and we have this opportunity, a part of the unique fact that we have now the high luminosity capable spectrometer. We have this unique feature that we can run our Drell-Yan program with both hadron positive and hadron negative beam. And this immediately gives you unique feature combining this data for pi minus induced Drell-Yan and pi plus induced Drell-Yan, basically subtracting these data set one from each other, you have immediate access. You can separate the contribution from the valence and see quarks. And this is really unique feature, and it is only available in case you can have pion positive and pion negative. If you have just one polarity, no way to access to separate contributions from C and valence. And yes, as it is written there, a part of this unique feature that we have the both positive and negative beams. We intend to increase the overall statistics, and especially in the sector of the hadron plus beam. And so far there was only one experiment, Na3, who has these two different signs of the hadron beams. And in blue here the points of Na3, and in red projections for AMBER. So you can see how much we can improve existing data. A part of the fact that all data, they are simply not accessible anymore. You cannot do physics with those data. And this is what is extremely important, that studying of the di-muon angular distribution, lambda, there are two competing processes. Because dielectron pair in the J side, in the J side, you can form J side through the quark annihilation or gluon fusion. These are two competing processes, and if Drell-Yan it is pure or anti-quark annihilation, J side it is a mixture of the quark annihilation and gluon fusion. So if you're clever enough and you know how to analyze your data, you can, using J-side data, you can have an input not only on the quark, the distribution inside proton and pion, because we have pion-induced J-side production, but also on the gluon contribution. And this is really very important. So there are different models which describe the relative contribution, which predicts relative contribution from gluon fusion or quark annihilation. For example, in the similar to amber, pion plus carbon process at 190 GeV. So you see, according to this model, the dominated contribution comes from gluon, but we wanted to separate it. We wanted to understand, we wanted to make this measurement in order to understand really what we can have there, because, for example, you see there are two models, SRMS, two factorization, SRMS and JAM, and they are equally good, nearly describe experimental data, but you see the totally different relative contribution from the gluon contribution and QQ-bar annihilation. So far data which were collected, they are not sensitive. They have no enough sensitivity to separate between the different the models. What we are going to do in amber, we are going to analyze as well polarization of the J psi in the final state, and this you can access just by the measuring so-called lambda parameter, lambda modulation in cos to phi, in cos squared theta, and this is really physics quantity which is very much sensitive to the contribution from the QQ bar or gluon fusion. So doing not only cross-sectional analysis, but polarization analysis in the final state, you will quite naturally define what is percent of the contribution in your J psi formation comes from the QQ bar annihilation, which from the gluon fusion. Similar job we can do for the kaon, because so 700 events. And this is the projection on the ratio between the up quark and the up quark and pion and the up quark and kaon. And in yellow bars you see the only available data so far, and in the pink it is what we will have in amber. If you access, you can also use the J psi from the kaon-induced in the kaon-induced experiment. And what is unique about this, because this is a components of the cross section. If you so you see, if you subtract from one cross section another, you just remain with a pure valence-valence quark contribution in proton and in kaon, because all the other terms, they are just cancelled. And this is really unique feature, how we can access kaon valence quark distribution in the J-side production. And of course, we can do as well physics with the antiproton or proton-induced Drell-Yan, because you would expect the PT distribution from antiproton much sharper, because according to the quark chiral quark soliton model, the C quark distribution in the proton, they have much wider PT distribution, and this is what we are going to establish comparing our Drell-Yan proton and antiproton induced data. Proton radius, you know this long-standing puzzle that the scattering experiment, they have a different result compared to the spectroscopy measurements. And here we can have a great job also as amber, because we use high intensity muon as a projectile, not electron beam, which scatters elastically on the proton. And if we are using heavy, the high intensity muon beam, we exactly became more sensitive to this very term, the electric form factor, which basically define you the proton radius. And the second form factor, which is sort of background, we have it suppressed because we have very good, because we have because we have very small, we have an access to a very small Q-square range. Because here, basically, Q-square range we can access. So we have very small value of Q-square. So this term is suppressed, and you became sensitive to the electric form factor. This is exactly what you have to measure. Apart of that, the great advantage of the muon beam, it is the fact that basically all electron scattering experiments, they were suffering from the radiative corrections, because electron light is a light particle, so corrections are huge. In our case, while using heavy projectile like muon, the radiative correction is suppressed by a factor, by order of magnitude. So, doing our measurement, I cannot say that we will we will set the point on this discrepancy between these two set of measurements, but we will do our contribution, because our experiment, it is experiment which is not similar to any one which was done so far. A part of the proton radius measurement, we can do as well the measurement of the pi and kaon radiuses. And this gives you exactly the direct access as well to the effect of the, or to the phenomenon of the emergence of hadron mass. The other measurement in this direction, in prompt photon production, we can have a direct access to the gluon component of the kaon, which is totally unknown. So basically, using our the features of our spectrometer we inherited from compass times, like electromagnetic colorimetry, we can really we can really isolate the single gamma in the final state. Of course, it is difficult measurement because the background is huge, but still, if we go to the high PT range, the PT above 4 GeV, then finally we succeed to suppress the background, and it stays lower compared to our signal. So not at all trivial, but feasible. And just to give you a snapshot of a bit different topic, its first measurement was, we have started amber because we have already took some data. It is a measurement of the antimatter production cross-section, so the antiproton production cross-section in helium. because we were able to do this measurement with basically unchanged compass spectrometer. All other measurements, they will require heavy changes. And why it was important? Because you know this nice data from the AMS experiment, which is somehow hanging upstairs, and measure the fluxes of the particles in the atmosphere. And what they were observed that they have measured, for example, antiproton flux with great precision. And at some point they said that it seems this flux is higher compared to what you would expect from simple nuclear interactions in the interstellar matter. But they surprisingly discovered that they cannot estimate the conventional flux of antiprotons from the conventional nuclear interactions, because no experimental data. No one was measured it with larger coverage compared to the, for example, LHCb. So this is the data we have already collected. We have collected this data with the different energies of the proton beam, incoming proton beam, and on the both on the three type of target: helium, hydrogen, and neutron. And now we are just analyzing this data, hoping to publish them soon. So what is about the future of the North area? Because you know it was constructed in 1974. And basically since then, our extracted beam lines was not touched. And you can imagine that after running for so long time, things starting to get apart. This is why very timely CERN approved this so-called North Area NA-CONS, North Area Consolidation Program, which will cost to CERN something like 200 million. So this is reasonable money, in order basically to refurbish all infrastructure of the North Area extracted beams. This means magnets, the beamline sensitive elements, control, and all the rest. Not only that, we convince CERN with our nice physics program for Amber, and we convince CERN to upgrade as well our extraction line, because our extraction line was basically optimized, because I said that it was a lot of muon measurement with a muon extracted beam has been done in our experiment line. And here is we start, this is extraction point from SPS, and this is the all line down to the entrance to the Amber experimental hall. The length of this beam line is 1.2 kilometers, with lots of various elements. And it was previously optimized for in order to extract muon beam. Now we have to have, we wanted to have hadron beams. What does it mean? Hadron beam is strongly interact particles. So we basically have to eliminate from our beamline, all in all, approximately 77 meters of air, which is distributed along the whole this extracted line in the various beamline elements. And this is what our CERN colleagues accepted as a request on the experimental side, on the experiment side. And they have now established the engineering change request, where they will address point by point all this what is depicted here. For all these elements, they will basically push out the air and insert vacuum tubes. A part of that, the CEDAR system, which is also CERN responsibility, will be refurbished, because as I said, our hadron beams, it's always a mix of pion, kaon, and proton. So you have to use this system in order to know for every single particle which is entering your spectrometer, whether it was kaon, pion, or proton. And thanks to effort of our Lisbon colleagues, of Katarina and Marcin, for the first time in the whole compass number history over the past 25 years, for the high intensity hadron beam, we see kaon component. And this is extremely important. This is absolutely essential for our future AMBER program. Yes, and planning the Drell-Yan experiment, you see now also this stuff, this bunker or sarcophagus around our production target will be constructed by CERN, because we are on-surface experiment. We have to stay compliant with the with the radio protection requirements. We have very high intensity hadron beam, so we have to cover our interaction point with the concrete protection in order to have to be able to extract high intensity hadron beam. So all this is on track, and this is the upstream part of the spectrometer as we have it for antimatter production cross-section measurement. I don't know whether I can run it or not. Yeah.
Monday, May 13th, CERN, under experimental area, upstream part of the spectrometer. We need be ready to start antimatter production cross-section day to day. This is a new setup we have constructed over the winter shutdown.
Yeah, so this is a setup which we use in the first part of this year run in order to measure antimatter production cross-section on the hydrogen and neutron target. So, no. This was the timelines of AMBER phase 1 till basically 2 months ago, 3 months ago, because we were thinking that we will run the antimatter production cross-section experiment, then we will run proton radius measurement, then we go in the shutdown at CERN in 2025. Now, yes, we learned that on the request of the LHC experiment, shutdown is shifted by 1 year, pushed back. So we immediately had sort of modify a little bit also our running plan, because you know you cannot be ahead of your schedule. You can only be behind of your schedule. So we certainly profit of this shift by of the long shutdown by 1 year. So still at this point we have finished our antimatter production cross-section program. So in the next 2 years, we will run proton radius measurement and preparatory tests for the Drell-Yan measurement, which we start after the long shutdown 3. Well, and talking about the sort of long-term plans, we think that the compass has established sort of achievement, a record for the fixed target experiments at CERN. It was lasting for 25 years. So this is sort of a target for us we have to exceed. We have to run for longer time. So now we start with the phase 1. It will be continued after long shutdown, and then we will jump in with our phase 2 measurements. So thanks a lot.
Thank you, Oleg, for this nice presentation. We passed a bit the time.
Yeah,
but I guess we
sorry.
have still opportunity for 1 or 2 questions. Not too long, please.
I did not understand very well if you use the same detector for amber as you use for compass, or
Not well. We did basically the same. We used the same experiment for the antimatter production cross section. That was just old compass spectrometer. Starting once we have finished this first measurement, now we change to the really amber spectrometer, because we change from triggered DAQ to the triggerless DAQ. That means that all our spectrometer we use so far, we at least have to rebuild the all front-end electronics, because our all front-end electronic, there are a number of very old detectors in compass we want to just to put in the garbage bin. But for this very last measurement, still we were sure we will survive for this 1 year something. But now for the proton radius measurement, we really change for the, and there are a number of new detectors has to be constructed for the proton radius measurement, like a TPC, like a new tracking detectors. All those new detectors, they will be already constructed together with a triggerless compatible DAQ front-end electronics. And during the long shutdown 3, and starting already from now, we are developing new front-end electronics together with a new DAQ in order to use these electronics for those detectors which are still in a good shape, which we can reuse in the amber time for all new detectors. And there are a number like GEMS, like cherry micromega, like new silicon trackers. All these new detectors we are sort of naturally already designed with these new triggerless compatible electronics. So fraction of the compass spectrometer will be still there, but small fraction.
Okay, any other question? Urgent? Okay. If no, we thank all.
Thanks a lot.